Xiang Xie, who actually can't be here. So this is going to be a pre-recorded talk, and he's going to talk about deploying TLS oracles using interactive ZK. So can we play the tape? And then he'll be here to answer questions, so we can still line up and answer questions just as before.
Yeah, hi everyone. My name is Xiang Xie from Pharmacy Labs. Yeah, I'm sorry that I cannot give you the presentation in person because of visa issues. So now today, my presentation is about deploying TLS oracles using interactive knowledge proof systems. So I think you may heard a lot about ZK TLS or web proofs or TLS oracles. I think they are all the same thing that we are talking about. So first of all, the background. So what is TLS oracle? What is ZK TLS? So in this case, the client has access to a server that can get their response from the server end. And the motivation is the client want to prove to the third party that this kind of data or encrypted data is actually from the intended server. The thing is that we want to do it without any modifications on the server side. And this is the most difficult part, because as long as we can change server side, the server can just sign everything and verify it. So yeah, this is the most difficult part. And in this case, we are considering the transport layer security TLS 1.2 or 1.3. And for example, the kind me who has a Coinbase account, I want to prove to another party that I have enough ETH actually in Coinbase, so without any help from Coinbase itself. One thing that is interesting is this problem was actually introduced by Dan from TLS Library about 10 years ago in a Bitcoin forum, that they are thinking about proving fiat transfers for P2P exchange of Bitcoin. And after that, a lot of academia papers came out to solve this problem, like Tom Creer, like Jacob, and our paper, Gabadan Proof. So all of these papers are trying to improve the efficiency in different trust assumptions, in different mode, and in different scenarios. First, let me briefly introduce the TLS protocol. So basically, TLS protocol has two phases. The first one is a handshake phase. In this handshake phase, the server has a certification, and the server and the client established a shared key using Diffie-Hellman key exchange, and using PRF or KDF to expand the shared key to different session keys. And as long as the client and the server have a shared secret key, shared session keys, they can communicate with each other using encrypted, using this different cipher suit. And here we are interested about this AAD cipher suit, or more specifically, AES-GCN. In general, so there are a lot of different ways to solve this problem. Like different people are trying to use TE, and in this talk, I mostly focus on cryptography modes. So in the industry, or what I'm talking about is more about this MPC TLS or proxy TLS. So MPC TLS means that the verifier and the client run a 2PC protocol to simulate a TLS client and talk to the server. In this case, the server actually cannot tell the difference if it's MPC simulated client or is it just a real client. And in the proxy model, the verifier actually sits between the client and the server, and the verifier forwards the transcripts, TLS transcripts between client and server. So the verifier just watch the ciphertext and record the ciphertext between the client and the server. So let's dig in a little bit of these two protocols. So first of all, in MPC TLS, I think the computation of circuits the verified client want to compute into PC is more about the key exchange, and here to PC on the key expansion or key KDA functions, which are a bunch of like shard circuits. The other thing, when they go to the handshake, when they go to the record parts, if the client want to send encrypted data, then the verifier and the client has to run to PC on AES GCN, because in this time the client and the verifier does not have the entire session key, so he has to run this to PC protocol with the verifier. And at the end of the protocol, especially when the verifier get the ciphertext from the server, the response from the server, the client has to run a general proof system on the KDF and AES to prove that he know everything, all the secret related to this kind of circuit. But this time, before they run the DKP, the verifier has to send back his key shares to the client, so the client had all the witness. So this is actually used by different papers, like Deco paper. They are using maliciously secure to PC protocols, which is authenticated Gabor circuit, and then they're using ZK snarks to prove the KDF and the AES. So we improve a lot from that paper, from that method, and we observe that only half gate Gabor circuit is sufficient, or only semi-honest Gabor circuit is sufficient, and including like we're using Quicksilver, which is interactive general proof system, to prove KDF and the AES. So the result of this Gabor improved system is that it's much efficient than the Deco paper in terms of computation cost and communication cost, and even memory cost. So in the proxy model, in the proxy TLS, so as I said before, the verifier sits between in the client and server, and this time the verifier get all ciphertext between transfer between client and server using AES GCM or other substitutes. So here the client only need to prove in the knowledge and show that he knows the secret related to all the ciphertext. And different papers are proving different circuits. So like in our Gabor proof protocol, we approve the KDF and the AES with Quicksilver, which is very efficient. And the other paper, like they are proving AES circuits with snarks, or proving KDF and AES, or char-20 with AES snarks. So it somehow bring more computation cost and the memory cost. So here are some comparisons of two modes. So in terms of trust assumptions and efficiency, for both MPC TLS and the proxy TLS, we have to trust the TLS server. Otherwise, you cannot do anything. Yeah. And the other thing that there should be no collusion between client and verifier. Otherwise, the verifier can cite anything, and the client provides. And one more trust assumption of this proxy TLS protocol is that the verifier has to make sure that he is actually connecting to the TLS server, the correct TLS server. Otherwise, a malicious client can then sit between the verifier and the test server to conduct a man-in-the-middle attack. In terms of efficiency, it's apparently that the MPC TLS has to run a two-piece protocol for KDF and the AES, which probably is the main bottleneck, efficiency bottleneck in a lot of products and protocols. And our benchmark will show that our product will show that it's actually the bottleneck when the user wants to use it. So the proxy TLS protocol can be much more efficient than the MPC protocol. So there's always a trade-off between this user experience and the trust assumption. So why, in this case, interactive zero-knowledge proof system is the best choice? So first of all, the protocol does not need to be fully online interactive. So TLS protocol itself is interactive, and the purpose is that the client proves will verify that the data is actually from the server. So interactive zero-knowledge proof system is totally suitable in this case. The second reason is that in both modes, the client has to prove KDF AES, which are all represented by Boolean circuits, and all these circuits are not zk-SNARK friendly. And in this case, actually the witness or the private data is actually owned by the client. So all these kind of client may deployed in different like resource limited environments like browsers, mobile devices. And the last one is that current zk-SNARKs have high proving time and memory use. And when the clients are deployed in a resource limited environment, then this may pose a major challenge in terms of like user experience. The client cannot wait for a long proving time, and it's always running out of memory, which is bad user experience. So yeah, we are using Quicksilver. Quicksilver is published back to 2021. It's an interactive zero-knowledge proof system, and it can prove Boolean circuits and arithmetic circuits. Especially, it's super efficient in terms of memory, in terms of proving time, and in terms of communication cost. So some numbers say that you can just in a very normal machine, you can prove 1 trillion AND gates within $2, which I think is amazing for for products. It's basically the cost is basically nothing. It's negligible for us to deploy this kind of system into our product, especially for like browsers and the mobiles. And in our global DEM proof system, we actually conduct a series of global scale experiments. So we deploy worldwide experiments in like 18 areas in the world, and we test when the users want to prove their data from Coinbase and Twitter. So all the numbers show that is quite efficient, and there's no like timeout problems issues when they connected to the data server. And we also prove that with proxy TLS using our like Quicksilver-based proxy TLS to prove very large content from large language model. For example, we can prove a 200 KB image that is actually generated from ChatGPT within 2 minutes. And this is experimented in the browser extension, not native machine, not mobile, not PC. So it's quite efficient. And when we deploy it to like mobiles or PCs, it should be much more faster. And this is the first one. I think this is the first scheme that can prove such a large amount of content from TLS server. Also, we built a zk-TLS benchmark framework, which is already open source. And in this framework, we trying to benchmark all existing open source zk-TLS implementations across different platforms and network conditions. And after we finished the benchmark, we found that our global DEM proof system is up to 10 times faster than other MPC TLS protocols. And also our Quicksilver-based proxy TLS is up to 30 times or 145 times faster than alternatives. And the TLS library, which is maintained by PSC, is a foundation, and a lot of TLS startup are using them, is now transitioning to Quicksilver, and I am one of the core contributors to implement this Quicksilver library. So we actually have a lot of products to support TLS oracles or ZK-TLS. So first of all, before that, we also build this tool, what we call is a developer hub, is to enable the developer to find any data from any website they want to prove using our ZK-TLS SDKs. So it's very easy for you guys, of developers, to find, okay, I want to prove my bank account, I want to prove that my social account. So it's very easy for you to get that web API and feed them to the SDKs. Of course, we have a bunch of SDKs, different SDKs. We have web SDKs to enable developers to build these web proofs, web applications. And also we have mobile SDKs that if you have apps in mobile, iOS or Android, you can use our SDKs to build that. Also, we have backend SDKs for you can use it to do a verifiable agent, and this can be run in a server or in the backend in a PC. Yeah, we deployed our product for a few times. So we already have more than 360K successful attestations. The users are just make it as prove their data. And 160K of these attestations are submitted to blockchain systems, like different blockchain systems, Ethereum, Linear, BNB, Scroll, Monad. And there is more than 540K downloads of our Chrome extension, and over 4K developer hub users to use it. And when we deploy our product, we do have a few challenges. So in order to bring better user experience for the users, our verifier or our server has to be globally distributed. The reason is that we want to enable the verifier to be positioned close to the client, because at this time, latency and the bandwidth are the main focus, or the main bottleneck to bring a better user experience. And the other challenge is that, as I said before, there is trust assumption, is about the collusion between client and verifier. So to mitigate this risk, and the best practice to trade off the trust assumption and the user experience is that we deploy the verifier within a TE. So it may bring some cost, but the cost is kind of negligible for us. But it also provides better user experience and to mitigate this kind of risk, and to make it much more, to reduce the risk, make it much more secure. Yeah, that's basically my talk. And thank you for your listening. And if you want to reach out to me, you can just scan this QR code, and we can talk, offline. Thank you so much.
Great, thank you. So is the speaker online to answer questions? Are you available to answer questions?
Yeah, hello, can you hear me? So yeah, I'm online and be able to answer questions.
Great. Are there any questions on TLS oracles? Can you say which one was actually deployed when you pushed these proofs on chain? Was it the proxy method or the MPC method?
Actually, both of them are used, but our default method is using the proxy method because it's more, it's much more fast. But we still have other options, like people or developers are using this MPC model. But yeah, it depends on the applications.
Mm-hmm. Yeah, makes sense. Well, all right. If there are no other questions, then let's thank the speaker again. Thank you very much.
Thank you so much.